Boilers with coal stokers are rare today, and this one is about to disappear forever. This is the last coal-fired boiler at North Dakota State University, soon to be replaced with natural gas. Today, we're touring the NDSU Heating Plant to see how coal is turned into steam and how that steam heats an entire university through miles of underground tunnels. We'll look at the stoker, the draft fans, and the feed water pumps that keep it all running. Hello, this is Jason from Steam, Electricity, and Propulsion. Let's take a detailed look at how they used coal to make steam to heat the North Dakota State University. This boiler was built in 1978 and is capable of producing 80,000 pounds per hour at 100 psi, and it has a spreader stoker made by Zurn. At different steam loads, different amounts of coal need to be fired. This is accomplished by a simple but elegant mechanism. To reduce coal consumption, the fulcrum point of these levers is shifted away from the cams. That reduces how far the coal pushers move, feeding less coal onto the grate without changing the overall speed of the system. Here is the ash pit room where they collect the ashes from the coal. Also underneath the boiler is the secondary air fan. It blows air through these tubes in the furnace to burn the volatile gases above the fire. You can actually see where the air is being blasted in through the flames. The purpose of the overfire air is to prevent black smoke and wasted fuel. You can see how clean the exhaust from the coal boiler is. Behind the boiler, there's the 350 horsepower induced draft fan and the 60 horsepower forced draft fan. Their max RPM is 1150, but they have variable frequency drives. Before VFD, they had to use dampers to control airflow to the boiler, which was slightly less efficient. This panel shows the air pressures in inches of water across the boiler. The furnace and stack are at a -1/4 inch. The induced draft fan is pulling about 3 inches negative, drawing flue gases through the boiler, while the forced draft fan pushes air in at about 1 inch of water below the fire. The overfire air is much higher, around 5 inches of water, because it has to penetrate directly into the flame to burn off volatile gases. Even though these numbers sound small, this is exactly how boilers move large volumes of air efficiently. High flow, very low pressure. In this back room is an abandoned draft fan from an older coal-fired boiler. That boiler was demolished in the spring of 2025, but the fan remains. A reminder of when coal was part of this plant. Next, let's see the feed water system, which is necessary for making steam. So these are the feed water pumps? Yep. In the basement, there are small condensate pumps that move water up to the surge tanks. From the surge tanks, the water goes to the 30 horsepower transfer pumps which fill the deaerator. The deaerator's function is to mix steam and water to remove dissolved gases to prevent corrosion and preheat the water. It sits just above the feed water pumps. In order to put water into a boiler at 100 psi, there are 60 and 100 horsepower, two-stage centrifugal electric-powered pumps that run at 3,500 RPM. These large and small feed pumps can pump about 350 to 600 gallons per minute and pressurize the water to over 200 psi. Water level is critical to boiler safety, which is why this boiler has a low water level alarm. During a blowdown, the drop in level will activate the alarm as expected. All of these major auxiliaries, the draft fans, feed water pumps, and other water pumps run on three-phase electricity at about 460 volts. This is standard for average-sized industrial electric motors. Now, let's venture up to the top of the boiler room. I have wanted to see soot blowers operating, so I asked Jeff, who was showing me around, and he was nice enough to demonstrate the soot blowers to me. First, he would pull chains to open the stop valves on the soot blowers. After that was done, the soot blowers were energized with steam. Then Jeff turned on the automatic soot blower.
Alright, we're gonna blow soot.
These soot blowers are manually operated. Jeff even let me blow soot. After blowing soot, here we are in the top of the boiler room. Up here is the steam drum, where the steam bubbling up from the boiler tubes is collected. Here is an amazing view of the college campus from the rooftop. All of those buildings are heated by this boiler plant. Now we're going to see the coal handling system. We're on top of the bunker, and this screw distributes coal into the bunker. Now we follow the conveyor belt down a narrow tunnel.
You get to hear it's a little bit of pain. I find it easiest to turn around, just bend over and back down, but
Bend over and back down?
Bend over, so.
Okay. I'm gonna be covered in coal dust when I go to work, but it's worth it.
At the bottom of the tunnel, we get to the roof again, and then go to the coal elevator, which raises coal up from the train cars. The steam you see blasting out of the small pipe is the deaerator vent, which is used to purge air from the water. These Quincy air compressors supply 100 psi air to the plant's automatic controls. They are rotary type compressors which are powered by 70 horsepower motors. We have seen all the machinery that works for the production of steam. Now let's see where it goes.
Is the Fargo Dome part of the campus?
It's technically owned by the city, but we sell.
This tunnel is almost a mile long and it goes all the way to the Fargo Dome. The pipe on the top is for steam and the bottom pipe is for the condensate returns. This system provides heat in the winter and hot water year-round, yet most people never see the beauty in the machinery that reliably keeps them comfortable. The era of the Zurn coal stoker here at NDSU will likely end in the spring of 2026, and I feel very fortunate to have been able to witness and share its final days of operation.
As the coal trickles down, it hits a rotary meter.
I'll continue documenting these boiler rooms and steam plants, and in the next video, we'll visit the new steam plant at the Valley City State University.